Hello everyone. I'm very happy to introduce Professor Narasimhan Soundararajan, who has very recently retired as a professor from Sultan Qaboos University, Oman, and he has been working in the field of applications of various geophysical methods for over 3.5 decades. He was earlier a scientist at the CSIR National Geophysical Research Institute after completing his master's, that is MTech in exploration geophysics, as well as PhD in exploration geophysics from Osmania University, Hyderabad. And after serving as a scientist at NGRI, he moved over to the academic position. He was a professor at the Osmania University since 2000 until 2007. Immediately after that, he has also served for a year. During this period, he has also served as a visiting scientist at Texas A&M University, USA, for a period of about a year. After that, he has moved over to Sultan Qaboos University, Oman, wherein he served nearly for about 15 years. After serving there, he has recently retired and settled down in India. We are very happy to have you, sir, today to enlighten our audience with your expertise, especially on magnetic methods as well as gravity methods. Thank you very much. Over to you, sir.
Thank you. Good evening to all of you. I'm Sundar Rajan. Okay. Now, let me talk about the interpretation of geophysical data in general. See, geophysical data interpretation is neither too simple nor too difficult, but sometimes it complex and deceptive. Geophysics students, even with people with the masters or PhD, all these qualified geophysicists can end up such a what do you call complexity. Why? Basically, the reason because of all this complexity of interpretation geophysical data is uh, because the physical properties which control the geophysical data or geophysical parameters vary in a different way, like exponentially, parabolically, linearly, randomly. So therefore, it's very difficult to have a analytical way how you interpret geophysical data. So as a matter of fact, I will start my introduction with a small Indian fable that reads, supposing, imagine that six blind men, when an observe an elephant, how do they feel? Each one, how do they feel? That's what it is. So the first one feels uh, the side of the elephant, it looks like a wall. The second one feels the tusk and he thinks the elephant is like a sharp edged weapon or a spear. The third one touches the trunk and thinks the elephant is like a snake, for example, this one. Then fourth one feels the knee, that is this one, and thinks that the elephant is like a tree. The fifth one thinks that the elephant touches the ear and feels that elephant is like a fan. Finally, sixth one feels that he feels this, he touches this one, that is grasps the tail and thinks it is like a rope. See, like snake, rope. So something like each one of them is correct because their imagination is perfectly correct. But collectively, when they discuss and think a lot of those things, they will not be able to come out. This is an elephant. The same way, the geophysical data, normally we don't confine to only one method or one interpretation method. So the entire data or the entire investigation has to be subjected to multiple methods of interpretation. Even then, sometimes it may completely be wrong also. So in which case, how geophysical interpretation is successfully carried out is a real challenge. It needs a tremendous insight, experience, skill, multifaceted talent, multifaceted understanding talents. For example, geology, geophysics, mathematics, physics, and soft computing, soft experience. All these things needs to have a fairly successful interpretation, if not 100% successful interpretations. Okay, so let me say like first, the geophysical first thing in the subsurface targets has to be realized. To some extent, it can be realized by means of shape of the curves, the shape of the anomaly, or the shape of the graphs resulted from the geophysical data when you plot them. See, for example, here it is spherical targets or cylindrical targets. See, one below the other. So it shows three different graphs. So what does this mean is, see, the deeper the one, the shallower the anomaly. The intermediate depth gives slightly higher anomaly. So the topmost one, that is with a very shallow depth, it gives a very sharp and large anomaly. So that way, it means that the geophysical target gives rise to the very broad predominant curves or predominant graphical what do you call display when the depths are at very shallow, and it is very low when the depths are at very deep. It's okay. So this is also another example. Now, the geometry, that is symmetry of the anomaly, is also controlled by its shape. For example, when the target in the subsurface is vertical, you will have a symmetric anomaly. When it is a slant, 60-degree slant means, the shape of the anomaly slightly tilts. It becomes an asymmetry. Again, in the case of 30-degree, see, it tends to be like that. The same way, the depth, for example, when the depth is about low, here the anomaly is predominant. In the same case, when it is slant, it gets tilted, it becomes an asymmetry. So all these things. So similarly, the same one, like when the target is very close to the surface, it becomes a very sharp, symmetrical. But again, it turns out to be asymmetrical when the target is slightly inclined. Like shape of the anomaly, another case is about, see, half width. That is the depth and the geometry and other physical properties are some of the parameters or some of the parameters needed for any geophysicist or for carrying out a mining or drilling or whatsoever it is. So how you'll be able to find out them is the interpretation. So interpretation constitutes at what depth the target lies and how big the target, what is the geometry of the target, and what is the physical property contrast. What do you mean physical property contrast is, say, for example, in the case of gravity, magnetic, that's what the subject of the study today. In the case of gravity, it is density. So the density contrast means, so this is what we call as a target, subsurface target. So this is surrounding rocks. So this is the surrounding rocks. So suppose the contrast is the density difference between the target and the surrounding rocks. So if this happen to be positive, the anomaly will be positive. If this is negative, the anomaly will be negative. So that I'll show you in subsequent pictures and all this. The interpretation, as I said, no, the depth, diameter, when you get the diameter, when you get the depth, when you get density, contrast, all these things, you'll be able to estimate how much is the volume and how much is the weight in terms of tons and all these things. So this is what. So the geometry could be anything, like either it could be a perfect geometry or it could be arbitrary shape. You cannot accommodate any geometry. So this is what the geophysical little bit difficulty in interpretation. So for example, we start with a few more examples. So this shows that when two different bodies lying adjacent to each other, for example, either sphere or cylindrical structures, when they lie adjacent in adjacent position, means each one gives rise to a peak. So when when the depth is very low. So when the depth is very large, so it becomes a flat anomaly. So by this way, you'd be able to understand, by seeing this, you'd be able to understand this one represent even one or two different bodies, but at a very deeper depth. Whereas here, two adjacent bodies at very larger depth. So that way one can infer by visual inspection, we'd be able to interpret to some extent. Then here, can we identify the targets again means, we'd be able to identify almost all the targets based on the geophysical. results, that is geophysical response, what we call response is here anomaly. Here, so this sort of anomaly is called are due to buried, faulted, thin slab. Fault is an important structure in geology. So when you take a gravity survey, when you do a gravity survey, the fault results a curve like this. So this is called a composite anomaly. Composite anomaly means total what you measure straight away and after connect corrections. In gravity, many corrections and all those things. Like there are about 7 to 8 corrections are there. When you apply all those corrections, the resulted anomaly is called composite anomaly. From which, so you'd be able to bifurcate or disintegrate into regional and residual anomaly. Residual anomaly is normally represent the shallow depth targets. Regional one represent the deeper targets. Say, for example, another case here, ice. How gravity anomaly looks like over ice. So this is the surrounding rock over which you find ice. The density of ice is only 1, and surrounding rocks could be anything about 2. So therefore, the density contrast is negative. So therefore, you get a negative gravity anomaly. So this is the thing. So by which you will be able to understand the target's nature, whether it is a high density or low density. Then limiting depth. So limiting depth is something like its concept which is needed in geophysics. So for example, as I said, the same example once again. See, these two are the first. This one is at a very shallow depth to adjacent spherical structures or cylindrical structures gives rise to 2 peaks. So when you still the depth is larger, the peak, it becomes much lesser. When it's still deeper, it becomes a single flat anomaly. So if you keep on increasing the depth, so it will become a flat, finally a straight line. So that means till such a time the response appears to your instrument, so you'd be able to call that depth as the limiting depth. So that's what. Why this is happening means in particularly the gravity anomalies decay with the inverse square of the distance from the source. So therefore, the relationship between the observed anomaly and the depth compute the limiting depth. So what could be the minimum depth at which the target lies is this one. Sorry, maximum depth. Then half-width method. So this half-width method is perhaps the oldest method of interpretation of gravity and magnetic data in geophysics. So oldest method means maybe about 150 years old. So with this method is still it is practically used. Yes, it is being used even in oil industry. Oil industry also is being used because in the dynamic modeling of seismic data, you always use gravity as an additional method. So when you model gravity data as well as seismic data, you need initial depth. So the initial depth is taken from this half-width method. So this half-width method says that when you plot the geophysical response, for example, in this case, a gravity response after all corrections, so the resultant anomaly, see, you measure the vertical distance, see exactly at half of the distance, you draw a line here. So this is the vertical line over this point at the point where it meets the curve. So this distance from the origin is called half width. So this half width normally approximately could be possible to approximately or equal to all the geophysical subsurface targets in the gravity interpretation. But however, sometimes it varies due to the nature of the geometry of the subsurface targets for spherical structure, for cylindrical structures, for irregular bodies, for fault, all these things vary. So some of the relations, empirical relations I just give here. In a case of spherical structure, it could be 1.3 times the half width. In the case of dipping sheet-like structures, it is 0.7 times the half width. For irregular bodies, that is arbitrary shape, so it is approximately equal to 0.86 times of the half width. For a cylindrical structures, it is exactly half of the distance. So like this, so this value is sometimes meaningful, sometimes close to the reality also. Similar to this, another method is being used to what is called is gradient amplitude ratio method. So the gradient amplitude ratio method is nothing but, so this is the gravity anomaly after all corrections. When you plot, this results the anomaly. Here in this case, for either 2D bodies or 3D bodies. For example, in the 2D bodies, for example, 2D horizontal circular cylinder, so the depth is always less than 0.65 times G maximum. This is called G maximum divided by G dash maximum. That is the gradient. That is dg by dx at this point is called maximum of gradient. So in the case of 3D bodies, for example, like spherical structures, prismatic structures, all these things, the depth is less than 0.86 times this ratio. So this is another method. So this is also very much approximated method. However, it is valid in most of the cases of gravity and magnetic anomalies. Then goes for the common or most commonly used geophysical method of interpretation nowadays is mostly mathematical methods. Some of the mathematical methods are very useful and they are very close to reality also at times. I don't say all the times, but at times. So one such a method is called spectral analysis. Spectral analysis is a Fourier transform based method. Fourier transform based spectral analysis is the application of Fourier transform. The Fourier transform is being used almost in all fields, engineering, science, everywhere. So here, when you plot the anomaly, take the log of the, that is after computing the spectrum, the computation of spectrum and all those things, it's a bit mathematical and you don't need. So all these features are available in the software. GeoSoft it's called. So GeoSoft interactive way of interpretation. Like you don't need to know mathematics behind it. You just know how to operate the software so that you'd be able to get it done. In which case, compute the spectrum, take the log of the spectrum. When you plot the log of the spectrum vertically and the wave number horizontally, if the subsurface targets or subsurface basin or whatsoever it is, if it is a multi-layered, means it will give as many as different straight line segments. The slope of each segment, so these are all straight line, this is another straight line, this is another straight line, this is another straight line. So each of this straight line gives a different slope. So the slope corresponds to the depth. That is, here in this case, it is 67.57 kilometer. The blue one is 33.85 kilometers. It is about 11.48 kilometer or 11.48 kilometers. Here in this case is 1.73 kilometers. So the depth to the bottom, if you want, so you'd be able to add up all these things and then say finally this is the depth. So this method is most commonly used almost in all gravity magnetic routine interpretation. Sometimes this method is even extended to another electrical, electromagnetic methods too. There are many case studies based on this. Then ambiguity in the interpretation, probably you might have heard about ambiguity in the interpretation. Ambiguity is uncertainty. So uncertainty of geophysical data interpretations is very common. Particularly in gravity, it is what you call theoretical weakness, what we call. What is the theoretical weakness is, because as I explained earlier, when the body subsurface targets is at a larger depth, you get a very weak anomaly. When it is a very shallow depth, you get a strong anomaly. Okay, that means the anomaly decays. It loses its amplitude depending upon the depth. So how the depth varies is, the gravity anomaly varies from mass of the body divided by square of the depth. That is mass m by d square, depth square. So this way it varies. So that's it. But at the same time, look at this picture. Here, this is spherical structure. This is another different structure. Here you see this is a structure. This is also another structure. So there are altogether all the four structures are there which respond only a single anomaly. So based on this anomaly, it will be very difficult to conclude what could be the shape of the or geometry of the subsurface target. Okay, here this is also the same case in a practical case. This is only theoretical explanations, but this is the practical explanations. So here in this case, so this is the target, including what you call target. This is surrounding rocks, but how this can give or this sort of depth can give rise to a geophysical response this way. So all these things correspond to one single geophysical anomaly means it's very difficult to imagine the target nature of the target. So this ambiguity of interpretation is almost everywhere in all geophysical methods, particularly gravity method. It's a theoretical weakness, it's called. But uh, based on multiple method of interpretations, one would be able to overcome this ambiguity to some extent. Then location of origin or subsurface targets. Location of origin is a concept in geophysics, particularly gravity magnetic interpretation. So what does it mean is location of the subsurface target, spatially where exactly it lies in the subsurface. So that's what called the location of the target. So sometimes we know that this is a location of origin also we say in this case. So how it is being done? In some cases, from the shape of the raw anomaly, that is corrected anomaly, you'd be able to know where exactly the source lies in the subsurface ground. But many times it is not so due to different geometrical structures or other way also. So there is a one method by which you would be able to locate exactly 100% exactly where the target lies in the subsurface for all the geophysical data, for all the geophysical methods, for all geophysical interpretations. So what is it called is amplitude of analytic signal. Amplitude of analytic signal is again a mathematical method. Here we use a mathematics called the Hilbert transform. Again, this is there in this GeoSoft software, so you'll be able to use. So this method also routinely used in the modern geophysical interpretations, including oil exploration. Also, this is being used as a ABO analysis. For example, oil exploration seismic data is predominantly being used, where the concentration of natural gas and oil can be spotted by means of highest amplitude. That is what we call as AVO analysis or bright spots. Then the amplitude of analytic signal, for example, so this is what called amplitude. What is this amplitude means? It is not the response of the geophysical data directly. We compute vertical derivative or horizontal derivative or Hilbert transform, whatsoever it is. Then anomaly, that is response square plus the derivative square taken square root. Then you plot this one, you get what is called the amplitude. When you plot this amplitude, the top here, this point directly corresponds to the subsurface target. So that means the target lies exactly below the top of this or peak of this response, that is peak of the amplitude. So this is what we call. So in which case there are two things are possible. One is when the width of the target, width means like horizontal direction. When the target is vertical or small, so in which case the width is B and depth is H. When the width is less than the depth, so you get a response like this in the amplitude. Whereas if the target is the other way, that is B is greater than H, that means width is greater than the depth. So in which case you get amplitude this way, that is two different peaks flanked by a minimum. So peaks, two peaks, one minimum. So this minimum corresponds to the center of the target. Okay, so maximum corresponds to two corners of the target, that is two edges of the target. So this is common almost in all bodies where width is greater than the depth. So these two methods, that is this method, analytic signal amplitude, is probably one of the very few methods where for all geophysical data, gravity, magnetic, electrical, electromagnetic data, the same concept applies. In other methods, you will have different approaches for different data and different anomalies also. Then modeling. So modeling I'll explain to you two case studies based on modeling at the end. So the modeling is either mathematical modeling or what you call numerical modeling or analytical modeling. So all these things is nothing but the measured gravity data or magnetic data can be compared with the theoretical anomaly. So it is theoretically you can generate the responses, compare these two with the minimum possible error. So in which case, if you be able to get a minimum possible error response by comparing the field data and the theoretical data, when the error results is, when the error is very minimum, so you'd be able to think that the parameters of the theoretical anomaly is equal to the parameters of the observed anomaly. So this modeling is very advanced. So you have a 2D modeling, 2.5D modeling, 2.75 modeling, 3D modeling, and all those things. So you may wonder, 1D model, 2D model, 3D model, you might have heard about, but what are these 2.5, 2.75 modeling and all these things? It is there, it's geophysical targets, sometimes you get such things. So what is the fractional geometry or fractional dimension is? There is a geometry called fractals in mathematics. So based on which you will be able to compute exactly what is the shape of the body. For example, suppose if you have a heart is 3-dimensional or 2-dimensional or 2.5 dimension means no, it's not. It's neither 3-dimension nor 2-dimension, but in between it is. So you'd be able to compute and then see what is the dimension of the heart as 2.175, something like that. The same way, the subsurface geophysical target, shape, volume, all these things can be computed based on this fractals mathematics. So this modeling, simplest terms I've explained to the modeling, but you can have several methods for this modeling. So certain models can result ideal results, certain models can be deceptive. It all depends upon how you compute, how do you iterate. So iteration means repeated. For example, suppose you start with one particular theoretical model, you match the practical data. So that means first time when you be able to do it, the error will be very high. Let us say 50% error. So this 50% error has to be reduced, means now you have to adjust the parameters of the theoretical target. How, for example, the model parameters, physical parameters, for example, density in the case of gravity, magnetic susceptibility in the case of magnetic. You need to vary in addition to other parameters needed in the modeling. When you model yourself, the software may ask you various parameters, so you'd be able to provide as and when you know in the field. So this way, when you adjust the density, when you bring down the density or increase the density, you'd be able to get another response. By this, all the parameters one by one vary. At one stage, you'll be able to minimize the error to 5% or even less than 5%. In which case, you'll be able to say you have had a best model or best estimate between theory and practical data. So this modeling we used in 2 or 3 of our practical cases, that is case studies. I'll explain you in the subsequent slides. For example, before that, I'll show you some of the modeling already modeled results. For example, here, this is the model surface where you have got water here, coal here, air here. Surface water has different density, air has a different density, coal has a different density. So when you take a gravity response, so the gravity response looks like this. That is practical cases. Okay. So this one, you'd be able to have a theoretical response. So that means your peak here, response is the same way. That to negative peak. So these negative peaks are corresponding to the air only, because when I say negative peak means your air's density is, so this one, and surface is this. Okay, sorry, it's also Gold's density, and Okay. So geological model, including water and air-filled voids. Theoretically, gravity anomaly point to this one top, and due to model. Observed anomaly is middle. If 22 microgoules is gravity unit of noise is present. So another important factor is all the measured geophysical data invariably is contaminated with the noise. So before you start interpreting, you need to reduce or minimize the noise. So there are a lot of methods in the software by which you'll be able to routinely process and remove some of the noise factors. So the depth of the layer is about 10 meter. Okay, so that is what this one layer is, about 10 meters. So this way, this model is explained. And okay, sorry, this one I missed it. So this one is I was explaining to you water, air's density is almost zero. Here, this one coal, and this one is water. So this is a response, and you get negative here because the density contrast is negative here. And here, this is water. Here it is sloping towards the ground, and if this is coal, you get a little elevated peak or something like. It's like so. So this one I had already explained to you. So now observed gravity anomaly over salt. Salt is a structure, geological structure, and this is one of the most favorable trap for oil and gas. So if you do a gravity anomaly, if you conduct a gravity anomaly, you have a gravity response like this. It is something like a spherical structure. Here, when you take a principal profile means take a line across this way and plot the gravity anomaly as a line graph, you get a gravity anomaly this way. So this is perfectly a negative anomaly. I say negative anomaly means the salt's density is very low compared to the surrounding sediments. So therefore, this one. So the half width here, it will work very well. Like so the half width of the method can give the depth to the top of the salt. Half width and the gradient amplitude ratio methods work well to estimate the depth to the top of the salt. This is another example of salt here. This is also observed salt anomaly, gravity anomaly over a salt. So this is what. So this results similar to the earlier one, negative anomaly. So this is what the subsurface target salt. The geometry of the salt is like this, various layers. So the anomaly width is about 3.7 kilometers. Okay, from which half width method can be calculated. And this is normally represent a spherical structure. So you'll be able to calculate the depth to the center is about 4.8 kilometers. And the density is about, radius of the sphere is about 3.8 kilometers. And assume the density contrast that is between sediments and the salt 0.25 gram per centimeter cube. So you'd be able to compute all the parameters like depth, it is independent of all this density and other things. Only from the shape of the anomaly you compute. But the volume you need, so the volume, it needs a density and represent the volume. Spherical volume is 4/3 pi r cube. So that what you call radius is needed. So from the radius, you'd be able to get the mass and everything. Finally, you'll be able to compute the volume and other required parameters. So the gravity anomaly or landfills, for example, landfill, how does gravity gives a response like this? So this is what called Bucher anomaly. So Bucher anomaly means, you must be quite aware of it. The measured anomaly, after all the corrections, the resultant anomaly is Bucher anomaly. So what is residual anomaly is, as I said earlier, Bucher anomaly is a composite anomaly. It consists of two components. One is regional as well as residual. Regional represent the deep-seated large structures, whereas the residual represent shallow structures, shallow depth, small structures. So that way, depending upon the target's nature, target's depth and other parameters, you'll be able to choose. Normally, residual gravity anomaly we interpret in most of the cases. So this is the residual anomaly. See how you'll be able to remove this. There are a lot of methods. How you bifurcate or how you disintegrate regional and residual. There are 7 to 8 methods. Simplest method is a graphical method that you must have studied in your basics. So now here again another example. See, this demonstrates that gravity response over a ore body. So this is an ore body. So whose depth is about 25 meters. It's a geometry. It is 10 meters radius. Rho is point, that is density contrast 0.5 gram per centimeter cube. See, the basement depth is about 225 meters. So in such a case, when you conduct a gravity survey, you get a response just like that. It's okay. So this response, you see over the structure, you get almost peak, like this is what. Whereas when the depth increases, you get the anomaly to be very weak, very strong, very weak. So this is how this geometry represents this gravity anomaly. Here you see the depth is only 200 meters. Here it is about 225 meters. So that is what the difference between this part and this part. It's okay. So here this one is due to this subsurface targets. So now look at in a practical case, gravity anomaly over a manganese ore deposit. Manganese ore deposit is very much possible in gravity and magnetic surveys or combine both methods. In general, geophysical exploration for any investigations, no single geophysical method ever gives exactly results which you need, or it can result a highly reliable results. Normally we combine at least 2 methods. In some cases, even four geophysical different methods are combined for single investigations, based on which you will be able to get highly reliable results also. Like the more the number of methods, the better the reliability. So that is the principle in geophysical exploration as well as investigation also. Like for example, here in this case, manganese, when you do a 2D gravity survey, plot the response, you get a contour. From this contour, how you get a depth means, so either how to do it means you need to draw a principal profile, a line either this way or this way, depending upon the nature of the contour, how it the shape of the contour. Here in this case, say it is almost like a spherical one. So therefore, through the sphere, okay, draw a line a dash. Now make the gravity value at this point wherever it intersects all the contours. Those points you take and plot a line graph. So you get a line graph like this for the manganese response. Now this is almost like a theoretical anomaly, but it represents the practical geophysical field data. So here, when you model it, how we model it means, see, for example, observed anomaly. Okay, so this is observed anomaly. And this dots, computed anomaly. Observed and computed anomaly is almost the same. So therefore, either mathematical method or the half-width method can give almost reliable depth and other parameters which we need. So this is what the shape of the anomaly is almost like a symmetrical or asymmetrical, totally asymmetrical. This kind of empirical method. So this way we call halfway method or amplitude gradient method. They are all called empirical method. From the shape of the anomaly itself, you estimate the depth and other parameters. So this gives, in such case, it gives almost, highly reliable interpreted parameters. It's okay. Here, another case is sulfide. Here, see here that the difference between the earlier one and this one is, here the sulfide ore gives rise to a different shape almost. So whereas I plot when this principal profile B dash like this way, as in the earlier case, you compute at each point of intersection and plot them as a line graph and compute the model. So when you compute the model and the practical anomaly, that is field anomaly, almost coincide. So therefore, the modeled parameters you'll be able to take as the parameters, that is the depth and other parameters to the practical or field data. Here, even half width method or gradient slope method also works very well here. So in all these cases, only the residual anomaly is used. So as I said, no, most of the cases residual anomalies are used for interpretation because these are all at very shallow depth. Then here, gravity anomaly or an abandoned mine. For example, abandoned mine means it's not an open mine; it's an underground mine. So, for example, sometimes when people mine it and without any precaution measures, if they abandon it, it's very dangerous for even human beings. When you work on the field or work on the area or for animals, everything. So in such a case, how do you detect the abandoned mine? Will geophysical survey is possible? Means yes, gravity method works very well. Like, see, look at this. This is the where you suspect the abandoned mine. Conduct a 2D survey, gravity survey, plot them as a contour. When you plot as a contour, the closed contours through which a line, as many lines as can be drawn, and see the modeling. So one such a model is line 3 here. It passes through most of the lines. Okay, so I take the value here, everywhere, and I plot and model it. So this is what the model. So when this model is calculated and observed is this int, the calculated is plus. Okay, so observed and calculated, they are almost coincide each other with very minimum error. That's what I said. Modeling, you can never have 100% fit or fitting. It is almost the same. So therefore, whatever the depth you get from the calculated value or computed model, so that remains that is equivalent to the actual depth. And again, from the shape of the anomaly, look at here. Everywhere it is like a flat almost. At this point, you see here, it's a negative. So this negative corresponds to the mine shaft. Okay, so where the density contrast is very less because open mine, closed mine means empty space. Therefore, the air is the air-filled mine. So the density is very low or zero. So negative, peak negative you get. So that corresponds to the mine. So therefore, then you'd be able to close them by all means. So that is how the modeling works, or the practical application of gravity in abandoned mine location works very well. Here, again, chromite. Chromite is one of the highest density or high density target. So here, so this is what Booger anomaly, that is after all corrections, the Booger anomaly, from which hardly you'd be able to locate the structure, or it's not possible to visualize or graphically visualize from this. So unless until you apply a mathematical method or some such things, you'll not be able to find out. So like then take the residual anomaly. So the residual anomaly pinpoints this particular area. Even this also still doubtful. That is the weak. Looks to be still weak. The contour values you'll not be able to read here because it's not given here. So in which case, how best I'd be able to enhance the anomaly, that is improve the strength of the anomalies? There are again a lot of mathematical methods. So one such a method is called vertical derivatives. Vertical derivatives, for example, first vertical derivative. See, first vertical derivative you take, it can pinpoint. Then if you want still improvement, you can go for second vertical derivative. Vertical derivatives, the higher the derivatives, the better the resolution. But at the same time, you are bound to lose certain information also. Wherever the derivatives are needed for the location interpretation, we use this sort of techniques. Then 2D gravity data, this already I've told you, but still I'm explaining here once again. So this is what we did a gravity survey somewhere in Muscat here, and just we wanted to interpret. So as many as, for example, when you do not know the pattern of the contours, you can have as many as principal profiles. So these three and this one, 4 different principal profiles are taken, and you model them again. First thing, you plot them and then see how does respond. For example, this one, this one, this one, this one. So all this responded in a different way, like from which depth if you want to calculate for each one, you need to model, or each one you need to able to apply any of the techniques. For example, uh, analytical method or spectral analysis, or one more method I'll tell you what's called the Euler deconvolution method. So any one such a method will be able to give the depth and other parameters in addition to modeling. For example, in this case, shown the modeling. Here, look at the modeling. Okay, so this is the model. The subsurface will be of this geometrical nature. So that is target with various density, various subsurface nature of the material. So all these things will give rise to a gravity response of this way. Okay. Another very important concept is called pseudo gravity anomaly. See, as I said earlier, no single geophysical method ever used in any exploration or any investigation. We combine at least 2 methods, sometimes 4, 5 methods also we use. How do we choose 4 methods, 3 methods, different methods, and all means depending upon the economy of the subsurface targets, we increase the number of geophysical methods. For example, sometimes in oil exploration, we use seismic method, we did a predominant method. So this can be sometimes, combined with the gravity method, magnetic method, or of late we use MT method, magneto-telluric methods. So all the 4 methods you can use extensively and get final results, and then process, interpret, finally they can come out with highly reliable results. Why can't they use? Because each geophysical method in the case of oil exploration is very, very expensive, because it covers a very large, wider area. So therefore you need to work for months together. So it is more expensive. So in spite of being expensive, people use these methods means because the nature of resource, oil and gas, it is very expensive again, and it gives a lot of boost. So therefore they don't mind to invest so much money. Whereas in normal mineral exploration, at least 2 methods will use minimum. For groundwater survey also, sometimes we use 2 methods, minimum 2 methods. Okay. Here in this case, gravity magnetic, if you want to use a gravity method, in some cases, the concept of pseudo gravity anomaly is being used. What is pseudo gravity anomaly? Pseudo means, like something true which is not true. That's what. Pseudo gravity transforms the total magnetic field anomaly into gravity anomaly. That means conversion of magnetic anomaly into gravity anomaly, or vice versa. Is it possible? Means yes, it is possible. Okay. So this is what it is. When you convert a gravity anomaly from this ambient field, so this one is it's a gravity field. So this is totally asymmetric. So this is okay, symmetric. Okay. Will it be possible this method, or to what extent it is reliable, converting from magnetic field, measured magnetic field? If you measure a magnetic field from one particular area, you don't need to measure again gravity method there. So on the other hand, you would be able to compute the gravity anomaly from the measured magnetic anomaly. So this is what called Poisson's relation. It is a mathematical equation is being used and computed under certain terms and conditions. So benefits, what are the benefits means? Gravity anomalies are often easier to interpret. Yes, magnetic methods, it's more complex than gravity method. The reason because the the magnetic anomaly is produced by different sources, whereas gravity anomaly is controlled by only magnetic density. So therefore it is easier, and more symmetric peaks centered over the source. Okay. Some structures, for example, mafic plutons produce both gravity and magnetic anomalies. So is it always possible? Means, so that is what not. It's not always possible under constant density and other subject to other variations also. So, but all practical purposes, it can work to some extent very well. Then again, as in the case of the gravity anomaly, The interpretation of magnetic anomaly is being also subjected to empirical relations based on the shape of the curves. For example, here for a contact, see the half width corresponds to 3.4 times h. Okay, whereas in the case of gravity, it is very simple. Look at here. For a thin sheet, here it is half width equal to corresponds to twice the depth. For example, horizontal circular cylinder. In the case of horizontal circular cylinder, in the case of gravity, it is just half width is equivalent to the depth. But here in this case, magnetics, the half width corresponds to 1.533 h, that is times h, like 1.5 times nearly, approximately. So that is what the variation difference between magnetic and gravity. But these relations too work very well in the case of magnetic anomalies. Okay. Now, 2D magnetic anomaly. I talked about all this gravity all this time, but you should remember that all the methods of interpretation, okay, it is almost the same in the case of gravity and magnetics. All the methods work very well, though gravity and magnetic are controlled by two different physical parameters. In the case of gravity, it is based on density. In the case of magnetics, it's based on magnetic susceptibility. But the method of interpretation is almost the same in all the cases, except a few, as I said in this case. So methods are equal, but values are different. That's it here. But in other cases, magnetic method for mathematical method, magnetic interpretation, whatever it gives, the same as in the case of gravity. So this is a magnetic response over somewhere near Turkey. The drilling locations and the position of the profile are shown. Solid circles denote the drilling that cuts the iron ore body. So these are all this one. So here this is the principal profile. Make it a linear graph of this one, model or use mathematical method, interpret, find out the depth, then you can mine it. So here, Kursk magnetic anomaly. It's a practical case. Kursk magnetic anomaly is a well-known iron ore deposit in Russia. Probably this is one of the largest iron ore deposits in the world. So this one, we interpreted sometime back in 1982 itself. Mathematical method called analytic signal amplitude. So the method itself is this is a observed anomaly after corrections. So this is what the computed mathematical tool called Hilbert transform or amplitude I said. So these two intersect at one particular point. So the point where it intersects, the distance, horizontal distance corresponds to the depth. So here in this case, about 25 meters. At a very shallow depth, you get about iron ore. And this represents one of the largest iron ore deposits in the world still today. Then we'll go on to our own case studies, like uranium explorations in India, in Chhattisgarh Basin it is. So it is when the recent past, early 2000, the survey was carried out. The survey was carried out by different methods because uranium is a very, very, very important mineral required for India. So therefore, the survey was conducted by AMD, Atomic Minerals Division, and the interpretations was carried out by my student as well as interacted with me for many suggestions, many interpretations and all. So yeah, combined effort has resulted this one. For example, this magnetic mapping was done predominantly by resistivity magnetic method, VLF method. VLF method means very low frequency electromagnetic method. This method is very low electromagnetic stations. You'll be able to find stations around the world. This VLF was used exclusively for military communications around the world. Okay, that is what called the chipsets. So for that is the primary method. The secondary method was the magnetic method. Okay, the resistivity method also was used. So each method has contributed its own importance to the entire interpretations. So for the magnetic method, the important petrophysical parameters are the magnetic susceptibility and remanent magnetization. Probably you know what is called a remanent magnetization. So these two, susceptibility and remanent magnetization, gives rise to the strength of the anomaly. So that is a high or low or strong or weak. So all these things corresponds to this. So the magnetic susceptibility of rocks is primarily dependent on the presence of ferromagnetic minerals. Ferromagnetic minerals, for example, iron and all. Okay, of which magnetite is the most common in the crust. So in this case study, magnetic method was applied as a secondary method with VLF-EM as a primary method. So resistivity as a third important method. So the measured magnetic anomaly only we will consider. VLF and all those things is altogether a different subject. We will not touch them at all. But final plot, it involves all the three. Even gravity was also used here, but gravity was not shown here, but only magnetic is projected here. So the measured total magnetic was used in modeling and inversion to decipher the assessment fractures associated with uranium mineralization in the Raigad district of Chhattisgarh basin. Okay, where is Chhattisgarh, and it was mined. It's being mined rather. So the results obtained from both magnetic and VLF data define the spatial locations and depths of fractures that agree well with the drilling data and are presented here as a case study. That means both magnetic VLF resistivity combinedly has given results based on which drilling was made. Fortunately, they have encountered the uranium deposit almost at the recommended depth. So this way, it is a successful case study. That means everything was done by AMD. So planning, survey, location, choice of methods, interpretation, and drilling also. So this way, a single organization doing all these things was something like amazing. So because they are concentrating much on radioactive mineral investigations or investigations. So this I'll show you. So this is what total magnetic field. Another important things you know about magnetic field, horizontal field, vertical field, total field, you must know about it. You must have known about it. See here, why do we need only total magnetic field? Why not be horizontal magnetic field or vertical magnetic field? It doesn't matter much. Any of the field, either you use horizontal or you use vertical or you use total magnetic field, you are bound to get the same results. Okay, there won't be any difference in the results. But suppose you measure from all the three magnetic field in one single geophysical one single magnetometer? Yes, I think Fluxgate magnetometer measures all the three, whereas total total magnetic field can be measured exclusively by other methods, other magnetometers. But nowadays, because of computational efficiency, if you measure one magnetic field, for example, suppose in the field you are measuring only vertical magnetic field, so you would be able to compute horizontal magnetic field and vertical magnetic field and total magnetic. Sorry, if you measure only vertical field, the other two components like vertical and total field, you'd be able to compute. In general, you call one magnetic field if you measure, the other two can be obtained by mathematical computations. That's what very simple. Whichever you measure, the other two. Okay. Total magnetic field recorded over a uranium deposit in Chhattisgarh basin. So this is the uranium is concentrated on this basement fractures. So this is the direction of the basement fractures. It is in Y-shaped. Okay. Basement fractures. This is the linear trend. Linear trend is this one. Okay. Represents the directions of basement fractures wherein concentration of uranium was traced on drilling. Okay, so this we published in 2007 in Geophysics. Here, as I referred earlier, the amplitude of analytic signal. Yeah, peak from the peak, we'll be able to get the location of the subsurface target, etc. And all. No, in the case of 2D, that is contours. If you compute the amplitude, it will give like this. See, look at this one and this one, you see it's how clear. So this is the concentration of uranium basement fractures. So this is the basement direction of the basement fractures where uranium occurs. So this is what. So the location is as simple as I discussed earlier. See, the direction of basement fractures is like a Y-shaped with linear trends M1, M2. So, okay, your response is also this way. Your amplitude of analytic signal is also this way. Clearly brought out by amplitude of analytic signal of total magnetic anomalies over uranium deposit. Okay. Here, the drilling results I'll show you in this. So here again, another way how you find out the depth. Earlier I explained, Fourier spectral analysis. Fourier spectral analysis is the application of Fourier transform. Here it is a single segment. Single segment means only one line is fitted into this. The slope of this line gives rise to the depth around 25 meters. Okay. Earlier, which I have shown in the graph, about 4 to 5 different slopes. All of them combinedly gives the depth to the bottom. Here, the uranium reached or encountered within this depth or slightly more than within the depth means we encounter here and still it may lie still higher depth also. Okay. The spectral analysis. There are another method of interpretation which I have told you about, Euler deconvolution. So for example, this is what Euler deconvolution. Euler deconvolution is yet another mathematical method in gravity and magnetic interpretation. Typically indicates presence of multiple potential sources. Multiple potential sources means, see here, each color, this coin-like shape of curve, each one represent one depth. So the each depth represented is uranium at different depths. That's what it means. Multiple sources. So this way, the depth varies right from 5 meter, less than 5 meter to greater than 50 meter. So uranium is occurring almost in all these depths. So that is how the Euler deconvolution works. And it depends upon at which depth the highest concentration, drilling will indicate that one. So depth obtained by Euler deconvolution method indicates the target lies in the depth range of 5 meter to 60 meters. Okay. Practically we talk about 60 meters. Again, this has come from the same publications. See, look at here, drilling results. Here, VLF, resistivity as well as magnetic. So, okay. So this one, the gray colored is the uranium deposit. Uranium deposit. Drilling is not vertical drilling, it's a slanted drilling. So like one drilling, another drilling, DPL1 and DPL2. So this both passes through the uranium deposit. Okay, so this is what the very successful case study implemented by Atomic Minerals Division, Hyderabad. So based on the estimated depths by various methods, the drilling confirms the uranium deposit on drilling at 2 different locations at a depth of estimated depths almost. Your 25 comes between these two. Okay, because there we have taken one line and computed one depth. Suppose if you compute several lines, if you have taken, you would have got several depths. Okay, so that is the difference between Euler deconvolution and spectral analysis. The sample depth. So within which you got uranium. That's how it is successful. It is. Then we'll move on to gravity modeling. Gravity modeling means the case study again, gravity case studies. So gravity modeling in depth and estimation based on basins. Basin again is another trap for oil and gas normally. So this is called Chindalpudi sub-basin. It is Kottagudem Kottagudem basin is somewhere near Godavari Valley. So how this is modeled means based on Margaret algorithm. Margaret algorithm is an algorithm in the modeling almost of all fields, not only in geophysics, every other field we use this modeling algorithm. Here, in gravity modeling, because your modeled response and practical data, practical field, so they almost they have to give minimum error. So what you need to do is, see, you assume one particular density, let us say, keep on decrease the density, depth, and other parameters. You try to get match, I said, for modeling. In the same way, in the case of density, in the subsurface density vary in a different way. we do not know exactly which way the density varies, whether it continuously varies linearly. Linearly means when the depth increases, the density increases, or depth increases exponentially, rapidly, whether it increases rapidly or slowly. So that we do not know. That's what called the exponentially. And randomly also, whether it is a randomly varies. There are so many approaches, 3 or 4 approaches are there. Like so, here in this case, 2 different approaches are being used for density variations. So the resulting depth of the model is about 2.84 kilometers. So almost similar to the drilled depth, 2.93. So this is very insignificant error. 2.84 kilometer resulted model depth. Whereas based on drilling, it was found, that is basement depth was found about 2.93 kilometers. The drilling was carried out by Oil and Natural Gas Commission as illustrated in the following figures. So in this gravity modeling, it's a bit difficult to see from the responses. It's okay. And another model is the gravity anomaly of the Pannonian Basin, Eastern Australia. So this practical data also being used for this model based on a mathematical method, our own method. So which was reproduced here for the modeling using different depth dependent density functions. As I said earlier, EDF, exponential density function, and parabolic density functions. Normally, linear density function is very simple. It's okay. So EDF and PDF when you use, so the mathematics become slightly tougher or complex rather. So here, same basin with 2 different density approaches, are they giving same results or different results? Okay, naturally they have to be little difference, insignificant error between these 2 methods. So the estimated depth by modeling is almost the same in both cases of EDP and PDFE, that range from 0.4 to 1.8 kilometer. So 0.4 to 1.8 kilometer in different places. Okay, so which I shown in the table, I'll explain to you later. Okay. Okay. So the highlight of the efficacy of this modeling is that the inverted depths are very close to the drilling depths available at 3 different locations marked as 1, 2, 3. Look at this. So this is what you observed in the results in the what you call table, whether 0.4 to 1.80 kilometer is reflected in the drilling table. You'd be able to visualize that. So the drilling locations are 1, 2, 3, which I'll show you later. See, like, this is what the Sindarbadi basin, that is Kottagudam or Krishna Godavari basins. Like, so this first one is observed gravity anomaly. Here and all, this one image, it's not like a contour from image produced from contours only. It looks like that. Observed gravity anomaly of the basin. Then this one is a modeled gravity anomaly. See here, as I said, your modeled gravity anomaly or observed gravity anomaly, they should almost look alike. When they look alike, your efficiency of model is proved. So this looks almost similar. So therefore, your modeling is almost highly reliable. Then third one is error between this and this. Okay, you cannot have 100% fitting match, or modeling and theoretical cannot be 100% match. So therefore, this is the error, minimum error in this case. Okay. Then estimated regional. So here the regional, how the regional could be estimated is, that is what 2 different regional estimated based on EDP and PDP. So that's what estimated regional background as a second degree polynomial and first bilinear equations. 2 different things are being used for this regional differences. So whether this regional response is useful here or not, just we wanted to show how this could be similar to each other. Okay, with the 2 different mathematical approach. Then F, plane view of the inverted density interface. Inverted density interface means depth wise, that is, this is what the contour depth inverted based on the modeling or our own interpretation technique. So this one has resulted the maximum thickness of the basin obtained from the present inversion is 2.83 kilometers and compares well with the borehole depth 2.93 estimates. As I earlier told you, this is what the difference. So the difference is about uh, 0.1, nearly 0.1 kilometer difference. 0.1 kilometer means it's about 100 meters or around 100 meters. It's okay. So around 100 meters difference between drilling and geophysical interpreted way is far, far less. So therefore, this is method is almost highly reliable, or you can say more than 95%, it is highly reliable. So that's what. But in all cases, you don't get it. Depends upon the choice of method you choose and how you obtain the data from the field, who acquires the data. So you should be able to take care right from the beginning to the end. If you do it, probably you'd be able to highly reliable results one might be able to get. Then the next one, Pannonian Basin, a gravity anomaly of the Pannonian Basin, Austria. So this is what 4 different methods here are there. Gravity anomaly of the Pannonian Basin is Eastern Austria. The location is Eastern Austria. This is what the measured observed anomaly here. Then this is the modeled anomaly. So modeled and observed has to be minimum error. So okay, error between observed and modeled gravity anomaly. This is what. So what is this is simulation of exponential density function with the PDF. Parabolic density model, I said, no, this one. Okay. Same way, exponential density model also is being used, but one is not shown here. So in this case, how you generate theoretically parabolic density model for subsurface Earth as deep as 10 kilometers, 15 kilometers. So you'd be able to do it. So this is how it shows. Okay. At shallow depth, see the variation is non-linear. Whereas at a deeper depth, the variation is linear almost. So that's what you can understand. So this we published in 2007 work. And here, the estimated regional and inverted density interface. Look at here. Estimated regional background, as in the case of the second degree polynomial bilinear equation, is are these two. Say they look alike almost, except broader width and lesser width. That's what. So minor. So that establishes the veracity of the method or modeling, whatever you can call. So the third one is plane view of the inverted density interface along with the locations of 3 boreholes. So this is what the inverted response. Inverted response means depth contour. See here, 1, 2, sorry, 3. The third one is here. Okay, this sorry, 3 and second one is here. So these are the 3 different places where it is drilled. So the drilling results, I'll show you here. Here, look at here. Borehole 1, 2, 3. First borehole 0.377 kilometers the depth. With the PDF parabolic density model, it has given 0.412 kilometers. With the EDF exponential density model, 0.398 kilometers. It's okay. So the error in this case is less than 5%. Sorry, 5% less than 10%. So that is what the error here. Percentage of error depth, no, it is given here. So second borewell, 1.175 kilometers drilling depth. What we got is about 1.011 kilometers. Here the error is around 0.16 kilometer, like I said. Here, in this case, 1.1. Okay, so 75 meters difference. Okay, so that's the reason why this error is slightly more here. Okay, so third borehole is about 1.624 kilometers. With the PDF, it is 1.5 kilometers. Here it is 1.75 kilometers. So the error is around, in this case, less than 10% is around 10%. So comparison of inverted depths with the ones obtained by somebody else also, this was interpreted, and they are almost the same with the borehole data. So this is what these 2 case studies, probably I think you got some of the facts and understood about. If you have any questions, you can ask me at a later stage or write to me. And if you have any other doubts on this also, you'll be able to contact me. So thank you very much.